Section 11.3 is called the integral test. What this section and the next section are going to take us through are several different types of tests that we can conduct to determine if a series is convergent or divergent. And what's nice about these two sections is it's taking us back to previous sections that we've covered, so it's a nice review on top of some new material. So this all begins, this integral test all comes from making a little sketch of some points connected with a sequence. So the idea here is, let's say we have some sequence where when n is 1, we just get this point. Now I'm actually going to turn this into a function, so let's just call this f of 1. And then when x or n is 2, we're right here. And then when x or n is 3, we're right here. So if it's just a sequence, we don't connect the points, but because I'm considering this or calling it a function, we will connect the points. So we'll get a curve that starts to look like this. But just keep in mind that a sequence is defined only at positive integers. That's why I'm only doing 1, 2, 3, and so on. But if I want to consider this a function, I can actually connect the points. And it's just to kind of make this point of how we're going to come up with this integral test. So let's say that the series, as n goes from 1 to infinity, of a sub n can also be written as, so the sum of a sequence here is the series. We could replace a sub n with f of n. And we could turn this into an integral. This is going back to Calc 1 when we first started to look at how integrals were related to areas under the curve. So if we have a right rectangular approximation, so if I make my rectangles here, I could find the area of each rectangle to find the integral. So this is going to actually, the summation here of all of these areas of the rectangles, there's some space or a gap right here. So I'm going to say that this is actually less than the integral from 1 to infinity of f of x dx. So this is how we could use the integral here. And the result of the integral is going to help us determine whether the series converges or diverges. So we're going to look at a theorem which explains this. So let's suppose that f is a continuous, positive, decreasing function. So those three conditions have to be met, and we're going to walk through. Sometimes we have to do a little bit more work to determine the decreasing part, but continuous and positive is going to be kind of easy to tell just by looking at our function. So again, let's suppose f is a continuous, positive, decreasing function on the interval from 1 to infinity. And let's let a sub n, the sequence here, just now be defined as our function f of n. Then the series is convergent if and only if the improper integral is convergent. And again, that improper integral is the integral from 1 to infinity of f of x dx. All right, so we're just going to do a lot of examples and kind of relate this, like I said, back to some ideas that we talked about at the end of chapter 7, which you're going to see. So pretty much all of our directions are going to be to determine whether or not the series is convergent or divergent. So let's take a look at the series written right here. So the summation as from n equals 1 to infinity of 1 over n squared. Now, again, with all of these problems in this section and in the next section, we need to provide the test we're using and explain our reasoning at the very end. So in this case, we're going to go ahead and let f of x become 1 over x squared. We always want to turn a sub n into f of x. So right now, we need to ask ourselves the three conditions here. Is this function continuous? Yes, there is, and we're looking from 1 to infinity. So if you recall understanding the domain, x cannot equal 0 here, but again, that's not from 1 to infinity. That's beforehand. So we would say f of x is continuous and positive. So whatever value from 1 to infinity we substitute in here, we're going to get a positive result. So f of x is continuous and positive. Now, technically, we could say it's the closed interval here from 1. We're including the 1 here, and that's okay, up to infinity. But now what we need to determine is f of x decreasing. So we have to go back to a Calc 1 topic and find the first derivative. Because remember, if our first derivative is positive, that means our function is increasing. If our second derivative, or rather our first derivative is negative, that means our function is decreasing on whatever interval. So let's go through and find f prime of x. So we could look at this as x to the negative second. So we're going to get negative 2x to the negative third, which becomes negative 2 over x cubed. Now, if we just kind of pictured some values here, when x is 1, that's definitely going to be negative. And for any value greater than 1, this fraction is still going to turn out to be negative. So we will say is less than 0 on 1 to infinity. We can include the 1 or not, it doesn't matter. Therefore, f is decreasing on 1 to infinity. All right, so we met our condition. So because of all of this, we can now use the integral test. So now this becomes the integral from 1 to infinity of 1 over x squared dx. Now we could reference going back to section 7.8, but I just want to go through this process again, and then we never have to do it again. We're going to come up with another generalized statement, the same that we came up with in section 7.8. Remember, 7.8 dealt with improper integrals, so this is a good review of that section. So we could say that this is the limit now as b approaches infinity of the integral from 1 to b of 1 over x squared dx. And we can now turn this into, again, x to the negative second, which gives us x to the negative first over 1, which becomes a negative 1, which becomes negative 1 over x. So then this is, the antiderivative is negative 1 over x from 1 to b. So now we're going to get a negative 1 over b minus a negative 1 over 1. And as b keeps increasing without bound, this is going to go to 0. We are left with the opposite of a negative 1, so we get a positive 1. All right, so now we're going to say since f of x, which is equal to 1 over x squared, let me rephrase that. We will say since the integral from 1 to infinity of 1 over x squared dx is convergent, the series from n equals 1 to infinity of 1 over n squared is also convergent, by the integral test. Now hopefully you recognize that it was 1 over x squared. So we would say, in general, the series of 1 over n to the power of p is going to be convergent for all p greater than 1 and divergent for all values of p less than or equal to 1. Again, we summarized that back in section 7.8. This is called a p-series. And we could always show, by going through the integral here, we can always support this. But now all we have to do is mention that it's a p-series. It's of this form, and then we compare p to 1, whether it's greater than or less than or equal to. So for instance, if my expression is 1 over n cubed, right away we could say that this is convergent because p is greater than 1. But if we had to really show why or how, we use the integral test. To prove it. All right, so like I said, we're just going to go through 5 or 6 examples. And all of these examples we are just answering, are these series convergent or divergent? All right, so in this example, we're going to look at the series of n over n squared plus 2. So first we have to figure out what is f of x. So we're going to let f of x just equal this expression with x instead of n. So it's x over x squared plus 2. Now, again, we're looking from 1 to infinity, so there's nothing that's going to cause any vertical asymptotes here from 1 to infinity. So we would say that this is continuous and positive on 1 to infinity, or we can include the 1. Now we need to find our first derivative. We do have to use the quotient rule here, so like I said, it's a good review going back to some Calc 1 topics. So we have low d high, so we have x squared plus 2. D high would be 1 minus high, and then d low would give us a 2x all over low low, so we get x squared plus 2, that quantity squared. Just go ahead and distribute, combine like terms. Well, this is just x squared plus 2, so we're going to get x squared minus 2x squared, so it's a negative x squared, and then plus 2 all over this denominator. Now in this particular case, we do want to ask ourselves this question. A lot of other times we're not going to have an issue here, but we need to figure out where our first derivative is equal to 0 or where it's undefined. We should always ask ourselves these two questions. So our first derivative is 0 when our numerator is 0. And I'm showing you this because of the result here. So this would become 2 is going to equal x squared, and x is going to equal plus or minus radical 2. Well, I need to be in this interval from 1 to infinity, so that just means I'm looking at radical 2. Now, radical 2 is greater than 1, so I need to make a number line here for my first derivative. So I need to show 1 and then radical 2. So let's say I were to substitute in like a 1.1. So, and I'm looking right up here. So if I had 1.1 squared and I took the opposite of it, 1.1 squared is 1.21. If I subtracted that from 2, I'm still positive here. But let's say I chose a 5. This will definitely give me a negative value because my denominator is always positive. So f is decreasing everywhere from radical 2 to infinity. So I can't say from 1 to infinity, but that's okay. We're going to connect the pieces here in a little bit. But going back up here, so if f is continuous and positive on the interval from 1 to infinity, it's still going to be continuous and positive from radical 2 to infinity. So again, because of those three statements now, we can use the integral test. So I know now I can write the integral from 1 to infinity of x over x squared plus 2 dx is going to equal the integral from 1 to radical 2 plus the integral from radical 2 to infinity. And this is the one I want to look at. All right, so we'll rewrite this as the limit as b approaches infinity, the integral radical 2 to b. Remember, integration techniques, we have to figure out which ones to use. Let's just start with u substitution. Let's go ahead and let u equal x squared plus 2. Then du is equal to 2x dx. So du over 2 is equal to x dx. So now this becomes the limit as b approaches infinity. We'll take the 1/2 out. We'll say as x equals radical 2 to x equals b, then this just becomes 1 over u du, because that x dx is du. Take the antiderivative here. So this will just become the natural log of u. Now because my x values are positive, I don't really have to worry about absolute values. But again, as x goes from radical 2 to b, then I could bring back in the x squared plus 2. From radical 2 to b. So now this becomes a limit as b approaches infinity of 1/2 of the natural log of b squared plus 2 minus the natural log. Radical 2 squared is just 2. 2 plus 2 is 4. So as b keeps increasing without bound, think of the graph of the natural log of x. It looks like this. So as our x values, our b keeps increasing without bound, this is going up forever. So then this just becomes infinity, which means the second integral is divergent, which means even if this is finite here, it's not going to matter because this one just kind of keeps growing there. So then we would say, so the improper integral is divergent. Which means the series, as n goes from 1 to infinity, of n over n squared plus 2 is also divergent by the integral test. So yes, these do require some work, especially for making sure f is continuous, positive, and decreasing over the interval that we're looking at. So our next example is going to be similar. There's going to be some algebraic work, some Calc 1 work that's involved. A couple of these are going to be nice, sort of short and sweet, and then we'll take a look at the last example is going to be a little bit more work as well. So again, now we're taking a look at the series of n to the 7th times e to the opposite of n, or negative n to the 8th. So here we're going to let f of x equal n to the 7th times x to the 7th times e to the negative x to the 8th. So again, if you think of the graph of e to the x, that starts to look like this. E to the negative x is just a reflection, but everything's positive here. And if we're just multiplying it by a power of x, especially from 1 to infinity, we're looking over here, that it's all going to be positive. So this is continuous and positive on the interval from 1 to infinity. Now we need to figure out what f prime of x is. We need to determine if this is increasing or decreasing. So again, this is y equals e to the x, y equals e to the negative x. That's not the entire function. I just wanted to go over the behavior of these two. So we're going to use the product rule here. So if I do uv prime, we're going to have x to the 7th times e to the negative x to the 8th times a derivative of that exponent, so negative 8x to the 7th. And then we have plus vu prime, so that's going to become 7x to the 6th when we take the derivative of the first part, times e to the negative x to the 8th. We want to clean this up. I'm going to multiply x to the 7th by negative 8x to the 7th, so that's negative 8x to the 14th. Over here, we're going to leave this alone. Now, technically, I could rewrite e to the negative x to the 8th as a denominator for both of these, and since they're the same, I can just put this over e to the positive x to the 8th. So now I'm going to go ahead and factor out an x to the 6th from the top, and we're left with negative 8x to the 8th plus 7 over e to the x to the 8th. So because we're looking from 1 to infinity, the only time this is going to be 0, let's still answer this question. The only time the numerator is going to be 0 is when x to the 6th is equal to 0. So that's when x is 0, and that's before the 1 to infinity. Or when negative 8x to the 8th plus 7 is 0, so this becomes 7 is equal to 8x to the 8th. So we get 7/8 is equal to x to the 8th, which means x is the 8th root of a number that's less than 1, so this is less than 1. So we don't have to worry about that. And the denominator is never 0, so f prime of x being undefined is never. So we don't have to worry about changing the limits of integration here. All right, so where is this, or the question is f prime of x negative on this interval? Because if it is, then that means our function is decreasing. So let's say when n is 1 or x is 1, we're going to get a positive here. This will be negative, and this is always positive. And anything larger than 1 will get the same result. So this is less than 0 for all x greater than or equal to 1. So f is decreasing on 1 to infinity as well. So we can use the integral test. All right, so now we say it's the integral from 1 to infinity of x to the 7th times e to the negative x to the 8th dx. We'll rewrite this as a limit, and then yes, we're definitely going to use substitution. So if you want to pause the video and give this a try to figure out the integral, go ahead and do so. It's going to be the limit as b increases without bound of the integral from 1 to b of x to the 7th e to the negative x to the 8th. So what we want to do, we want to let u just equal this exponent, negative x to the 8th. That way du is going to equal negative 8x to the 7th dx. And du over negative 8 is going to equal x to the 7th dx. And that's this part right here. So in a way, I want to say the hard part's over. We've been doing this next part so much, hopefully that you feel this becomes a little bit easier than what I just had above that. So now this becomes, again, since I'm using u substitution, I want to say x equals 1 to x equals b. We could take that negative 1/8 out in front, and then we just get e to the u du. And as we continue, since the antiderivative is just going to be e to the u, I could bring u back in. So this just becomes negative 1/8. The antiderivative is just going to be e to the u, so that's e to the negative x to the 8th as x goes from 1 to b. So we get negative 1/8, and I can rewrite this as 1 over e to the positive x to the 8th, so this becomes b to the 8th, minus 1 over, this becomes e to the 1 to the 8th, so just e. And as b keeps increasing without bound, this denominator is getting larger and larger, so this value goes towards 0. And now I'm just left with a negative 1/8 times a negative 1 over e, which is a positive 1 over 8e, which is a finite number. So again, we're going to say since the improper integral in this case converges, or is convergent, the series is also convergent by the integral test. All right, just a few more examples, and our next few are very short to the point where we don't have to go through this whole process. All right, so what makes this one much shorter, straight to the point, is this expression that's right here. This is a p-series because it's 1 over some power of n. So what we do is we point out what is p. In this case, p is radical 7. We compare it to 1. That is greater than 1. Therefore, the series is convergent. That's all we need. Short and sweet. Now, we're not always going to be given the expression, so you may be given an actual series written out. So let's take a look at this one. So the trick here first is to be able to write it as a summation. So I'll give you guys a moment, see what you can come up with. All right, and pause the video if you need more time. So the idea here is to figure out what our denominators are doing. So the first one is just going to be 1. And if you took a look and maybe tried to square each integer value, well, 2 squared is not going to be 8, but 2 cubed is, and then 27 is 3 cubed, 64 is 4 cubed, so this becomes a summation from n equals 1 to infinity of 1 over n cubed. Then it looks like this form for a p-series. So that's what we would want to write out. This is a p-series. Where p is equal to 3, which is greater than 1. Therefore, the series is convergent. Let's try another one. See if you can write out the summation for this. All right, pause the video if you still need more time. But this would be the summation as n goes from 1 to infinity. If you take a look, we're taking the square root of everything because this would be 1 over the square root of 1. So it's 1 over the square root of n, which can also be written as 1 over n to the 1/2. And again, this is a p-series. But what is p in this case? It's equal to 1/2. How does that compare to 1? It's less than. Therefore, in this case, the series is divergent. Because p is less than 1. Those are nice ones to work with. All right, we'll just try one more example. Here are series. Definitely not a p-series here. We're going to go from n equals 3 to infinity of 7n minus 6 over n squared minus 2n. So now we're back to what our first couple examples are. So let's take a look and let's let f of x equals 7x minus 6 over x squared minus 2x. Now remember, we're going from 3 to infinity, so we have no issues with our denominator when n is greater than or equal to 3. So this is continuous and positive on the interval from 3 to infinity. Let's find our our first derivative. Again, let's use the quotient rule. So we have low d high. So d high is just going to give us 7 minus high d low. We're going to get a 2x minus 2. Because these are two binomials multiplied together after a minus sign, I want to keep those in brackets. Over low, low, so we get x squared minus 2x, that quantity squared. Let's distribute. We're going to get a 7x squared minus 14x. And as I multiply these two together, we're going to get a 14x squared. We're going to get a minus 14x minus 12x plus 12 all over our denominator. Combining like terms, 7x squared minus 14x squared is a negative 7x squared. This minus 14x, this will turn into a plus 14x, so those are gone. So next I'm left with a positive 12x minus 12 all over our denominator. So yes, technically we should set our numerator equal to 0, see where that works. But again, we just want to know if this is negative for all values 3 to infinity. So if I try to 3 here, that's going to give me 3 squared times a negative 7 plus 12 times 3 minus 12. So that's going to give me a negative value. And then any value larger than 3 is still going to result as negative because we're squaring it, multiplying it by a negative 7. And then our denominator is always positive. So this is less than 0 for all x greater than or equal to 3. Therefore, f of x is decreasing on the interval from 3 to infinity. So we can use the integral test. So let's see how this one plays out. So we're going to set up the integral from 3 to infinity of 7x minus 6 over x squared minus 2x. Now in this case, we can actually factor that denominator. And as we do that, this allows us now to use partial fractions. But again, if you weren't sure, you could try use substitution and see how that works out for you. But always look to see if you can factor that denominator, then we would want to use partial fractions. So we are going to set 7x minus 6 over x times x minus 2 equal to a over x plus b over x minus 2. And we'll solve this for a and b. So we could say a times x minus 2 plus bx is going to equal 7x minus 6. So when x is 0, we're going to get a negative 2a. It's going to equal a negative 6, so a is 3. And let's let x equal 2. A is going to go away, so we will get a 2b. This will give us 14 minus 6 is 8, so b is equal to 4. So now the integral from 3 to infinity now becomes 3 over x plus 4 over x minus 2 dx. And we proceed from there. So now we'll say this is the limit as b approaches infinity. The integral from 3 to b of 3 over x plus 4 over x minus 2 dx. So now this becomes the limit as b approaches infinity. We'll get 3 times the natural log of x. And again, because all of our x values are positive from 3 to infinity here, we don't need the absolute values. So we'll just get the natural log of x plus 4 times the natural log of x minus 2 from 3 to b. Substituting in, we now get 3 times the natural log of b plus 4 times the natural log of b minus 2. Minus, we'll get 3 times the natural log of 3 plus 4 times the natural log of 1. So what's going to happen with these first two terms as b keeps increasing without bound? They do as well. So this is divergent. And we could say then the series is divergent since the improper integral is divergent.